hopefully this evening. Back to angular momentum. So we kind of, remember, last class, our target was the hydrogen atom. And we realized that the hydrogen atom, in order to represent its physics and understated structure, is we have 3 dimensions that we have to deal with, which we converted into spherical coordinates, which gives us this r parameter, this distance parameter, and 2 angles. All right, and I want to continue exploring. And what I told you is that this will lead us to separate the problem, that the hydrogen atom can be represented as a product of 2 solutions, one that's only dependent on r, the distance between the proton and electron, and one that's dependent only on the angles, or the relative orientation of the electron with respect to, say, the z-axis of the atom. And so I want to focus in particular on that angular part today. And I talked kind of intuitively last class. Where we should tackle this is looking at angular momentum, right? The momentum of rotating something. And I wrote it down really quickly last class that we can relate angular momentum to kinetic energy, right? Ultimately, what we want to do is write down a kinetic energy term for our hydrogen atom as a function of the angles. And the way that we're going to explore that physics is through angular momentum, the idea of the momentum or the energy of having something orbit something else in an angular fashion. And so I wrote some equations down at the end, kind of roughly. I'm going to go back to them and we'll recap what we learned. And we'll take that information and we'll dig into it. All right? We'll understand the quantum mechanics of angular motion, rotation, and we'll come up with a couple of really, really useful equations that will give us insight on how to deal with the hydrogen atom. All right? Once we have that, we can apply it directly to this problem. And then we have the problem of the radial part to solve, which is the part about the Coulomb potential, the electrostatic potential, which is a function of r. So we have to deal with that. So that won't be something we have to worry about until next week. All right, so we'll focus just on angular momentum today. This is a topic near and dear to my heart because my PhD and my research is, and what I do is I use light to spin molecules. I rotate molecules. So this is the theory of my research. I'm not going to really talk about molecular rotation in this class unless we have some time near the end, because it's not super, I don't want to say it's not super useful because that would sell me short, but it's not necessarily the biggest focus at the moment. What I want to do is take that rotation theory and apply it to the hydrogen atom, and we'll also apply it to spin. And I think that's a much more kind of pedagogically and conceptually much more evocative example than talking about how molecules rotate. Okay, despite the fact that molecules rotating are very interesting. And I could talk about it for an entire year. So, the idea is that we have this system, just like our diatomic from before. It's got a center of mass, two masses on the end of something that's fixed at length r. All right, and in the case of a hydrogen atom here, one's the mass of the proton, one's the mass of the electron. Or you can think of this as atoms. It doesn't matter. The theory is exactly the same. And the idea was that the angular momentum of this system is this number I, which we call the moment of inertia, times the angular frequency. So this is actually, sorry, I should be very careful about this. This is the magnitude of the angular momentum, because frequency and moment of inertia are scalars. It's not a vector. Where the moment of inertia is like an effective mass. It's a rotational mass, an inertial mass. And for a diatomic, for a two-body system, like we have on the board here, I is equal to the reduced mass of the system, mu, times r squared. Okay, so let's just look at mu really quickly. Remember that mu is the reduced mass. And let's look at it very briefly for the proton and the electron system. Okay, so if mu is me, so let me rewrite this generally. Remember, the reduced mass is this product of the two masses divided by the sum. By the way, I saw some people on homework 3 do it the other way around. Luckily, the number that you get for HCl for the reduced mass is about 1. So the inverse of it's about 1, 2. So you weren't that far off, but I saw some people wrote m1 plus m2 over m1 times m2, which is the inverse. All right, so what does this look like for the proton and the electron? So for P and E, we have the mass of the proton times the mass of the electron times the sum of the masses. Right, but what did we say about the mass? I said about the masses of the proton and the electron last class. The mass of the proton divided by the mass of the electron, the mass ratio is about 1,000 to 1. Okay, so if the electron has mass 1, then the proton, right, if the electron has the same mass as the hydrogen atom, I think I said this to you guys, maybe it's the other section. If the electron has the mass of a proton, sorry, I started to forget. If the electron has the mass of a hydrogen atom, the equivalent mass of a hydrogen atom, that means the proton is larger than any existing atom in the world, in the universe. Right? There's a huge difference in mass. Right? If you think about the heaviest naturally occurring element, that's uranium. Uranium has a mass of about 238. And so the ratio of hydrogen to uranium is 238. The ratio of the proton to the electron is 1,000. That's quite a big difference. All right, so this is a bigger gap in mass than anything. Right, so the idea is that compared to the mass of the proton, the mass of the electron is negligible. Right, so for this, mu kind of looks like the mass of the proton times the mass of the electron, but when you add the mass of the electron to the mass of the proton, it barely changes it. Right, so you have MP, and then you have this little tiny ME term that we can go to 0. All right, we can just assume that it's neglected. Right, and so what does this end up being? Well, the mass of the proton cancels out, right? Because we end up having MP times ME over MP. And so that means that the reduced mass is effectively the mass of the electron. Okay? So we don't have, when we talk about the hydrogen atom, we don't have to worry about reduced masses because the proton doesn't contribute at all. The proton just sits in the middle. The center of mass is right inside of it. The only thing that determines the angular momentum properties of the hydrogen atom is just the mass of the electron. That makes things a little bit easier for us. Now, we can't make this assumption for anything. We just can make this assumption for the proton and the electron because they're so much different in size. Okay. And then we have one more term. Oh, okay, so so the moment of inertia for the hydrogen atom, therefore, is MER squared. Okay, and then we also have the angular frequency, which is this omega. Right, and this is the angular angular version of velocity, right? Instead of it being how many meters you travel in 1 second, it's how many radians do you travel in 1 second. So the units of angular frequency effectively is radians per second. Radians aren't a real unit, so we usually just say it's per second. Okay? So angular frequency in particular is radians per second. Now there's other types of frequencies. A typical frequency, like the one that you represent in hertz, like in Planck's law, E equals h nu, that's the amount of time it takes. That's how many times you go 2 pi per second. Okay, so it's slightly different, right? So nu, like E equals h nu, is a frequency of an entire period. How many periods do you go through? How many units of 2 pi do you go through every second? Whereas omega is how many radians do you go through 2 seconds? Right, so they're just related by a factor of 2 pi. The idea is that omega is 2 pi frequency. 2 pi the frequency. Okay. So that's how we relate frequency in terms of energy and angular frequency. It's just a factor of 2 pi. So it's important to keep those distinctions because sometimes you'll be off by a factor of 2 pi in calculations. I don't think it's a big deal here, but it's something to note. This is also why, I just want to make a mention, this is also why there's h and h bar, is that h is the equivalent of, remember it's E equals h nu, right? So h converts between frequency in terms of 2 pi radians, how many times you go around a circle per second, to energy. Right? That's why it's E equals h nu. But if it were E equals h bar, you would replace v with omega because it includes that 2 pi. Right? So h bar tells you how to convert radio frequency, which is radians per second, omega, into energy. And h, it converts you between period frequency, how many times do you go around a circle in 1 second, to energy. Okay, so that's the difference between h and 2 pi, h and h bar, is this factor of 2 pi. You're converting between radians per second and 2 pi radians per second, or circles per second, revolutions per second. So they're just different by 2 pi. So that's why sometimes you see, for instance, when you see equations where you have h in the numerator and then there's some factor of pi in the denominator, you can always put them back together and just get h bar. That's that extra 2 pi. You're converting between radial frequency, which is the number of times you go around a circle, and angular frequency, which is how many radians do you move per second. So just different by 2 pi. It's a small change, but an important one. Okay, so we have to take this is all classical, right? So we need to find some way to convert this into a Schrodinger equation to solve. Right? We need to solve the Schrodinger equation for this problem. And so that means we have to write an energy down. So what's the energy of this angular momentum? Well, I mentioned this at the end of the last class. I'll just remind you, is that the kinetic energy, T, is equal to the square of the angular momentum divided by 2 times the moment of inertia. Okay, and I kind of justified why this is the case, is that if you let I equals mu r squared, then T is equal to mu squared, well, let me write it like this, mu r squared, or sorry. So angular momentum is mu r squared omega, and this is all squared, divided by 2I, which is mu r squared. And what you end up getting is 1/2 I omega squared. And this is just kinetic energy, but now we've just made all of the terms a little funky. Remember that linear momentum, right, moving something in space linearly, right, like me walking across that, right, the kinetic energy is 1/2 mv squared. And we have the same kind of form here, that the kinetic energy of rotation, or of angular momentum, the angular energy of something rotating, is 1/2 times its effective mass, m, or I here, times its velocity squared, its frequency squared. Okay, so the math of angular momentum is almost precisely the same as forward motion, except now it's in a circle, instead of it just propagating through space. We're fixed at a fixed position, fixed r, and we're just forwarding in a circle, but all the math kind of works out the same. Angular momentum aren't so much different from regular momentum. It's just that we're now confined to a circle instead. Okay, but if the kinetic energy is equal to L squared over 2I, well, all we have to do is now, if we want to promote these things to operators, quantum mechanical operators, that means that L squared over 2I, the operator for L squared, whatever that is, the way that we measure the angular momentum, is related to the operator for kinetic energy. But we know how to write that. Right, so what this is saying now is that L squared over 2I for the hydrogen atom, we're going to be specific about the hydrogen atom, which is L squared over 2 mass of electron r squared, is equal to minus h bar squared over 2me times what we call the Laplacian operator, which is just the second derivative with respect to position. Right? It's the kinetic energy we write down every single time we write a Schrodinger equation down. Right? Minus h bar squared over 2 mu times the second derivative with respect to position. Right? So our quantum mechanical measurement for L has something to do with our kinetic energy. Right? So we don't have to think about necessarily what L looks like, because this already gives us a formula for what the operator for L looks like. Right? It's just related by this factor. We have to multiply a few things around, but L is related somehow to the kinetic energy times h bar squared. So L squared, let's just do a little bit of math, is equal to minus h bar squared r squared times the second derivative with respect to position. But once again, we have a problem here. Is that right? Yeah, that's right. Once again, we have a problem here. We have an r, and we have Cartesian coordinates. Remember, r is equal to the square root of x squared plus y squared plus z squared. And then we have these Cartesian coordinates, right? This is a messy equation. Right? So automatically we're starting to see, maybe this is a good point to stop for a second and say, well, this is why Cartesian coordinates are a really poor choice for angles. Because we know that all that's happening to this system is it's just rotating like this, right? So why should we track these three independent coordinates that are linear in space, right? That track something that's fixed in position that's just rotating in a circle. Right? It's just a meaningless, it's not meaningless, it's just kind of an unnecessary way to tackle this problem. Because this is very useful for linear motion, right? When you have an object that starts here and ends up over here, this is a very natural way to do the physics. But if you have an object that stays here and all it's doing is rotating like this, well, it seems excessive to worry about all these coordinates. All right, so this is why we convert to spherical coordinates and angles, because that's the natural, right? That's the natural parameter for rotation is an angle. All right, so what we need to do now is we need to take this operator, this complicated thing, and convert it into spherical coordinates. Right? We came up with the conversion factors between x, y, and z for each of the coordinates, r, theta, and phi. And if you do a bunch of chain rule, and let me tell you, the chain rule is nasty. I'll never make you guys do it. I had to do it when I was an undergrad. To take this and convert it into spherical coordinates, and you get a new operator in terms of r, theta, and phi. All right, so what we want to do is transform this now to a better set of coordinates. Right, because we really want to talk about r, which is a fixed quantity, right? It's a rigid rotor. This thing is not stretching. It's fixed in place. So we want to transform to spherical coordinates. Okay. And so when you do that, I'm going to write down this really, really scary equation. It looks ugly, but we'll be able to see how things start to fall apart. It's not too bad, all right? But it's just a long equation. All right, so I'm going to try to write it here.
Like I want to test the Excel equation.
So what I want to do in particular is I want to convert just the derivative part of the expression into spherical coordinates. That's the problematic part. The rest of it's written in terms of r. So what we need to do is get rid of the x, y, and z. Right? So we want to change this into our spherical coordinates. And just like in Cartesian coordinates, we have three terms. X1 and X1 and Y and 1 and Z. We're going to have one that's dependent on the derivative of R, one dependent on the derivative of theta, one dependent on the derivative of phi, the two angles in the radius. So we'll have three terms still, but because of the chain rule, they start to look a little ugly. All right, so I'll write it down for you. And this is not an equation I'll ever have you work with, but I think it's important to look at it because it helps us understand a little bit about the structure of the math. So there are three terms. I'm going to write them separately. First, we'll write the term dependent on r. So it's 1 over r squared times the derivative with respect to r of r squared times the derivative with respect to r. So it looks like that. So that's our radial term, right? If you look. Now, because of the chain rule, the derivatives, right? So the way this works, instead of it being the second derivative of x, where you take the derivative of the derivative, we have to take the derivative of r squared times the derivative of our wave function. So there's this extra factor of r squared that's sandwiched between the two derivatives. And that's just because of the chain rule. Right? The way to convert between x, y, and z and r, we get this extra factor of r squared. But you can imagine that if I could factor this r squared out, it would cancel out here, and I would just be left with dr dr, which is just the second derivative with respect to r. Okay, so that r factor is just there because of the chain rule, but as you can see, it all cancels out. Once you can kind of manipulate it a little bit. All right, now we're going to do the theta term. I'll do it in a different color. So there's 1 over the r squared sine theta. We have a constant term on the outside. Let me make this a little cleaner. R squared sine theta times the derivative with respect to theta of sine theta times the derivative with respect to theta. Okay? Again, the idea is similar here. If I were magically able to pull this sign out, it would cancel out with this one, and I'm left with something that looks like d theta of d theta, which is the second derivative of theta. Right? But there's this extra term sine theta because of chain rule. Right? And we're left with one last term, which is the phi term. And it looks kind of similar. It's 1/2 r squared sine. Oh, let me write this a little bigger, guys. Sorry. 1 over r squared sine squared of phi. Oh, sorry, that's wrong. Sorry, it's sine squared of theta. My bad. Times the second derivative with respect to theta. Okay. So on the theta term, it just all the chain rule cancels out. We don't have this ugly derivative of a derivative thing. We just have the second derivative of phi left over. All right. So again, this looks really, really, really nasty, and it is. But the thing is that what we've done is we've made our equation more complicated, but we've reduced the complication in terms of how the coordinates talk to each other. Because each of these terms effectively are only dependent on motion along one of the coordinates. They're all separate, right? This is only dependent on changes in r. This one's only dependent on changes in theta. This one's only dependent on changes in phi. Right? It looks just like this, right? Where you have a sum of an x, a y, and a z. They're independent of each other. Right, but we have some additional constant terms due to chain rule that makes this look really ugly. But the physics are exactly the same. We've converted to this more useful set of coordinates that will actually simplify quite a bit once we make some adjustments to it. Okay. So there's a term for this. If you're like me and you like to read the textbooks, you'll see a couple different names for this thing. This is what's called the Laplacian, which is a mathematical term. And sometimes you'll see it called del squared. It's an upside down triangle with a square sign, and it's an operator. So it's called the del operator. Okay, it's a very, very common in differential equations when you're looking at changes in things in space, over time or over space. The Laplacian is very common. Solving the wave equation for classical waves has a Laplacian in it. It's a very common mathematical operator. But it's basically just the second derivative of the function with respect to its coordinates. But because of the chain rule, we get all these ugly extra terms. Okay. So, but we've made it look more complicated, but now we can actually stop for a second and think about how does the system evolve if we fix r and we vary the angles, or we fix the angles and vary r, which is what we want, right? Remember, the potential energy is only dependent on r. It has no theta dependence, right? So we're going to be able to deal with the theta part separately from the r part, which is exactly what we want. Okay, so let's look at this a little bit. So I know you guys are probably still writing that stuff down, but it's okay. We'll keep going. So the important thing is that we're going to assume the thing that we've assumed, what's called the rigid rotor approximation, which is that R is unchanging when L is not equal to 0. Okay, so when we spin the object, the assumption is that the bond doesn't stretch. All right, now I want you to go try to give a slinky at home. Take the edge of end of a slinky and spin it around your head, and you'll know the harder you spin it, the more it stretches. All right, so a slinky is not a rigid rotor. It's very obviously not a rigid rotor, but by and large, molecules up to about a factor of 1 in 10,000 are very rigid. So when you rotate a molecule, it barely stretches at all. So as you move the system an angle, the change in R is 0. Right? The bond doesn't stretch from what we call centrifugal forces. Right? There's no centrifugal force effect. There is a centrifugal force occurring on the molecule trying to get it to stretch, but the molecule effectively doesn't stretch. All right, so what does that mean? So this means R is unchanging, which means, of course, that the derivative of the wave function with respect to R is equal to 0. Okay, so that means that any derivative of the wave function or of your system with respect to the radius is unchanging because the radius is unchanging. The bond length, or the distance between the proton and the electron, is unchanging. So if I just go back just a quick second, and we look at our Laplacian here, this big result here at the end, right? D by dr is 0. So this entire term disappears for the rigid rotor. Okay, so when we freeze the system and we say that the electron is at a fixed distance from the proton, we don't have to worry about this first term because this all goes away. D by dr goes 0 because R is not changing. So that means that the angular momentum of the system, assuming it's rigid, which is a good approximation, it turns out, only depends on d by d theta and d by d theta and d phi. It only depends on these two terms. So for a rigid rotor, so for our system, so for the P plus E system, the hydrogen atom, the Hamiltonian for the angular momentum, so we'll call that the rigid rotor, the angular part, we'll call that the angular part. Remember, we have a radial part and angular part. We'll call it angular. Is going to be equal to minus h bar squared over 2 me r squared times 1 over sine theta d by d theta sine theta d theta plus 1 over sine squared theta d by d phi squared, like so. All right, all that r part goes away. Now if I write h psi is equal to e psi, what does that look like? Right, because remember, this is going to be, the Schrodinger equation says this is equal to e psi, and we want to put the psi here. So where does the psi go? Well, we operate right to left, so the psi goes here and the psi goes here, like so. All right, so what we need to do to find the wave functions for this system is we need to find the wave function such that when we take these derivatives, we get the wave function back times the number. And this will give us the wave functions for the rotation, right? The properties of the rotational behavior of this electron. But as you can see, that's not an easy problem to do. Okay? So, in fact, the solutions of this are actually well known. Okay, so this problem was actually solved about 200 years ago. Now, not for quantum mechanics, but Maxwell, the electromagnetism people, discovered this differential equation, something very similar to it, that leads to the same solutions. Where you find the solutions to this is if you have a charge, say an electric field, that's contained on the surface of a sphere. Well, that seems a lot like an electron, right? Right? So you have, so in classical mechanics, so let me actually just draw this. So quantum mechanics, so this equation has same solutions as for electric fields constrained on the surface of a sphere. Okay, so if you have like a, maybe you've seen those Van de Graaff generators, those spheres that have the charges that come in, the little lightning bolts and stuff, like you touch your hands and lightning bolts get attracted to your hands and stuff like that. So think something like that, where you generated the electric field, and the electric field, it exists at all points along that surface, okay? On the surface itself. And if the system is spherically symmetric, the way that the electric field looks like, where are the maximas, or where are the oscillations of the electric field, what are the values of the field on this sphere, it can be determined by the solutions of this differential equation. So instead of thinking about the wave functions of an electron moving around on a sphere, which is what we're looking at, remember we fixed r, so this electron is moving around a sphere of radius r, has the same kind of physical behavior, at least in terms of the equation we need to solve, as if you were to charge a sphere, put electricity on the sphere and have it conduct, and you get the same kinds of solutions to what the field looks like as you do for the wave functions of the electron. It's the same functional form. Obviously the interpretation is different, but this gets to that wave-particle duality thing again. Is that the solution of an electron at fixed radius looks like an electric field confined on the surface of a sphere. Right? What's an electric field confined on the surface of a sphere? Well, that's just electrical waves propagating on a sphere. And here we have an electrical body, the fundamental electrical body, an electron, propagating it as a particle on the surface. Right? So you can think of it either way, but one of them is exactly equivalent to the electromagnetic application. But in fact, there's no, it's obvious why they have the same solution, because it's the same thing. One's particle, one's wave. There's nothing, in some ways you could say that there's nothing different. A large macroscopic sphere that you touch that is charged is really nothing different than a sphere, fixed radius, that has a bunch of electrons moving on it. It's just a macroscopic amount of them that act like a wave. So the solution is not really any different. So we'll go appeal to our forefathers and foremothers for the solutions of this problem. All right, and the solutions are really, really beautiful. All right, so we're going to solve this equation. Solve h psi equals to e psi for a rigid rotor. Well, and what it actually is, just a minute. Where's my circles tool? What it really is the solution to having a little proton in the center, a little proton. And let me just kind of draw this like it's a sphere. Sorry. Come on, stop doing that. There we go. All right, so we got this sphere here. Right, a fixed distance r. Right, and there's an electron here that's fixed on this surface, and it's just orbiting around in some direction around this surface. There's different trajectories, if you will, stable trajectories of this electron on this sphere, if you will. Right, and the wave functions represent these stable trajectories of the electron on this sphere. So the idea is that the wave function, I'll just write that again, is that, so this is the classical picture, that it's an electron moving on a sphere that's centered with a proton inside of it. Right? And this says that the solutions, the wave functions, which should be functions of the angle, are equivalent to stable trajectories of an electron on a sphere. Okay, again, this is all qualitative, right? I haven't written down any formulas or anything like that, but that's the interpretation that we have here. Is that these wave functions represent unique solutions with different energies, of course. Each one will have a different energy and a different behavior and appearance. And I would like to show you some pictures of them in a second and also write them down. Let me just, I don't quite have the prep here. I just need to look at the formulas really quickly. And I want to show you what these look like. And when I draw some pictures of what these functions look like, these wave functions look like, you're going to be like, I've seen these before. And we'll start to see that you're going to start to see the hydrogen atoms start to take shape here. I just needed to get the formulas for them because I always forget them. And they're tabulated. I think I have a page on Canvas of all the different solutions for this, but we'll go through it later. We don't need them at the very moment. Okay, so let me go to the next page real quick. All right, so what are the solutions, right? We have two things that we need to know. We need to know the wave functions, which are theta and phi, and the energies. Right, those are the two things we care about. Gosh, I didn't place a formula here anywhere? Come on. All right, I'll find them in a minute. I apologize. All right, and so the wave functions, they have a very specific name. I'm going to give you the symbol for them first, and I'll give them a name. So the symbol we write them is a Y. Let me do it in a different color. So these are what are called the Y, and they have two indices. All right, remember the harmonic oscillator has one quantum number, V. Particle in box has one quantum number, N. The spherical harmonics have two. I'll explain what each one represents soon, okay? But for the matter, you can imagine that the angular momentum problem, because it's a function of two coordinates, it has two quantum numbers. All right, and we'll see that one quantum number is associated with motion around phi, which is around the z-axis, and the other one has something to do with theta, which is dependent on all the different directions. All right, so it's going to be like this magical total number and then this projection along the z-axis. But I don't want to talk about that just yet. We'll see that very soon. But the idea is it has two quantum numbers. The one quantum number is called J, and the other one's called M. And these are functions of theta and phi. They're two-dimensional angular functions. All right, and these functions are called spherical harmonics. There's a good reason why they're called spherical harmonics. Remember, we learned with the harmonic oscillator, we got these harmonic equations, these unique solutions, this bell curve function times a polynomial. These are the harmonic oscillator functions, right? That's for linear harmonic motion. These are the functions representing harmonic motion on a sphere. They are not necessarily related to the harmonic oscillator, but the idea is exactly the same, as we'll see. The reason why they're called harmonics is in some ways in the same energy as why the harmonic oscillator is called a harmonic oscillator. Now, I'll write some down. I'll write some functions down in a few minutes. All right, but let's look at the energy. So the energy is a function of just one of the quantum numbers, J. And the energy of this is h bar squared over 2 times the mass, the moment of inertia, times the quantum number J plus 1. J is what's called the total angular momentum quantum number. All right, and j can be any positive or zero integer. Okay, and then there's also, all right, so that's j, but there's also this m quantum number here, which we haven't discussed yet. And we'll see what that actually, this m means in a second. Or I don't know if we'll get to it today, but we'll come back to it. It's not super important right now because the energy is not dependent on it. M is called the azimuthal, or the projection angular momentum quantum number. And M has a very interesting behavior. It runs from minus j to minus j plus 1 all the way to j minus 1 to j. Okay, so the value of m is determined by j. All right, what does that mean? Let's think about this structure for just a little bit, okay? So the idea is that each Jm pair has a unique wave function. Okay, and how many m's are there per j? Well, if j is equal to 0, then there's only, right, m can only be between minus 0 and 0, so there's only one. So only m equals 0. But if j is equal to 1, there's going to be 3 states. M equals plus 1, m equals 0, and m equals minus 1. Right? And I can just keep going. Right? There's going to be 2j plus 1 degenerate states. Right? They have the same energy per j. Now, this sounds very complicated. You've seen this before. And you've seen it in the hydrogen atom. You've seen it in every atom you've ever looked at. And let me draw you what these functions look like. Right? I won't write down the formulas yet. We don't have to worry about them right now. Okay? We'll talk about the wave functions and the formula for all these next week. Okay? I just want you to think about them a little bit. We're going to kind of look at them abstractly a bit. And then when we really need to start interrogating the wave function, we'll start thinking about what they look like and what the functions are. They're not complicated. They're going to be functions of sine and cosine. So they're going to be sine theta, cosine theta. Sometimes they're going to be sine theta times cosine phi. They're just functions of sine. They're just sines and cosines. Nothing too crazy. So let me draw. I'm just going to draw some pictures for you of what these look like. So let's start with the easiest one. Jm equals 0, 0. Right, and I'm going to plot these on a polar plot. So the x-axis will be theta, and the y-axis will be phi. All right, and let me show you what these spherical harmonics look like. So for the j equals 0, m equals 0, which is what we call the ground state, right? It's the lowest energy state, j equals 0. Looks like this. Actually, let me just draw it as an actual circle. It's a circle. It's completely circular. There we go. This is the let me change that actually. So let me change this. I apologize, guys. Let's just change these to Cartesian coordinates just to make it easier for you. This will make it look better. So we'll just choose 2 coordinates here, z and x. Okay. So this is the harmonic. This is what the spherical harmonic looks like for the 0, 0. All right. So this is a circle. So if you have a, and I should actually say this is squared. Sorry, this is the square of the wave function. some of them might be imaginary. So let's take the square, right? We've always measured the square of the wave function. So when we look at a rotating object, let's say an electron bound to a proton, and its ground rotational state, its ground angular momentum state, it looks like a sphere. Now, if you are a big nerd about electronic structure and atomic orbitals, you probably know what this is representing. You've seen this before. But let me show you the J equals 1 spherical harmonics, and then maybe it'll start to make sense to you what these are and where this comes from. So again, I'm going to do X and Z. It's just easier to think about things in terms of what they look like in space. And there's 3 of them, right? Remember, there's 3 M states for J equals 1. So I'll draw them like this. Let me just do one more box. Let me make these boxes pretty. I'm sorry. All right, so this is the J. Oops, sorry. This is J equals 1. We'll call this M equals -1, M equals 0, and the M plus 1. It doesn't really matter. And we'll see why in a second. And let me finish the coordinates for these other ones. So this is along, we'll let this one be XZ as well, but I'm going to change this 1 M plus 1 to X and Y because they're perpendicular to each other, as it turns out. All right, so the M equals -1 looks like this. And again, this is the square. Here's the M equals 0. And here is the M equals 1. All right, so this first one is y1 minus 1 squared. The spherical harmonic. This one is y01 squared. Sorry, that's a bad 2. And this one is y11 squared. All right, someone yell out. What do these look like? Exactly. The structure of the S and the P and the D and the F orbitals, right, there's globe-like shapes, come exclusively from the angular momentum part of the electron. So what you say, so this is what we call an S orbital, or what the electromagnetic people call an S wave. Right? Remember, the solutions look exactly the same for the electric field on a sphere. So the S field, if you will, the S wave for the electric field on this is the same as that the electric field has the same value at every point on the sphere. That's what the equivalent would be for the electric field. And these, again, have that lobe-like structure. There's going to be a region of your electric field along these axes of your sphere that have a higher charge, and there's going to be regions where there's no charge. Right? So this is what's called an S. An S wave. And what would the J equals 1 one's called then? If it's not S, it's what?
P.
Exactly. These are P waves. Exactly. We have not considered, remember, the important thing is that this is just a geometry, right? This sets the geometry of the orbitals. We still haven't considered the fact that the electron can move in terms of R, right? But just from the angular part, we get the S's and the P's, and of course, if we go to J equals 3, we'll get the D's. And we go to J equals 4, we'll get the F's. And they look exactly like you would expect them to look. We have not considered the radial part. Right? But remember when we talk about hydrogen orbitals, right? I'm giving away the answer, but maybe it's starting to become clear here, is that remember when you write about atomic orbitals, you have the 1s and the 2s and the 2p and the 3s and the 3d, right? I haven't talked about that number yet. The 1, the 2, the 3. Right? I've only identified the S, the P, the D, and the F character. So where does that 1, 2, 3, 4 come? 1s, 2s, 3s, right? There are multiple S waves for different n's, for these different levels. That number, which we call the principal quantum number, n, comes from the radial part. All right, so n equals 1, n equals 2, right? 1s versus 2s. Those are distinct orbits of different radii, if you will. But each one has its own set of spherical harmonics. Right? And we'll also find that, again, n and j are related to each other, right? Because there's no 1d orbital, right? There's only a 1s orbital. So the maximum value of j is going to be dependent on n. We'll see that later. But in reality, we haven't figured out that structure yet. But again, all the structure that you know from atomic orbitals comes from the fact that they're of the angular part, right? And the radial part of the wave function, which we haven't dealt with yet, gives us the n quantum number: 1, 2, 3, 4, 5, 6. Okay. This structure, these are spherical harmonics, ubiquitous. Chemistry and physics. I get the same solutions regardless, right? In my research, I spin molecules in space. Whole molecules, 20 heavy atoms spinning in space. What do their wave functions look like? Look like spherical harmonics. Of course, they're a little funky looking because molecules are not perfectly symmetric and spherical, but their solutions can be represented as a sum or a linear combination of spherical harmonics. So a normal diatomic molecule or a normal molecule, its rotational wave functions look exactly like these. They're completely universal. Right? Anything that moves with an angular dependence in a spherically symmetric way in space has this kind of wave function dependence in terms of its angles. Right? So that's where the S and the P and the D and the F come from. It is completely encoded. But the best part, the thing that's amazing, or the thing that I love about angular momentum is we had that really, really complicated operator. Right? The really nasty equation. And we haven't looked at the formula for the spherical harmonics yet. They're not too hard. And there is a formula for them. You can calculate them and come up with a formula for them, but we're not going to worry about that too much. But the energy is just so simple, right? It's just every energy level has a number j. It could be anywhere from 0 to 1, and the energy is dependent on jj plus 1. Right? And you're going to see that jj plus 1 come up everywhere. Because we'll get the spin, for instance, with the hydrogen atom, or the electron spin 1/2. Like I keep mentioning spin, we haven't talked about it really. We're going to find that the energy of the spin is SS plus 1. And then we talk about different types of other angular momentum molecules or atoms, and they all have this JJ plus 1 dependence. This JJ plus 1 comes up everywhere. Right? It's like a fingerprint for the energy of rotation. Very, very common, right? It's just like that V plus 1/2, H bar omega V plus 1/2 that we have for a harmonic oscillator. This is really, really complicated math, but it all simplifies this beautiful harmonic formula. And that's exactly what we get here. So we had to do all that nasty legwork at the beginning, but it ended up giving us something really elegant and very geometrical as well. We were taking advantage of the symmetry of the sphere, and we get really nice symmetric solutions. Okay. So the one thing I haven't mentioned yet is this other quantum number m. Now, what you can probably identify from the drawings I've given here for the different harmonics, right, this kind of looks like, if you look at the j equals 1, the p waves, right, you can kind of say, oh, this might be px, this is pz, and this is py, or something like that, right? Right, so that the m is going to determine which orbital it is, or which orientation the solution is. M tells you something about the orientation of that rotation. All right, but I want to specify very clearly where that number comes from. Okay, what is it measuring? What is m actually measuring? J measures the total angular momentum of the system, how fast it's rotating. What does m measure? We're going to have to deal with vectors a little bit to answer that question. So we're going to decouple J and M with vectors. Okay, so what we have to do in order to start talking about angular momentum in terms of vectors, we need to define the angular momentum vector. All right, so I'm going to go back to I'm sure if you had Nick Popolowski, he probably taught you this a million years ago. I learned it a million years ago, is that the angular momentum vector is r, the r vector, right, which is the kind of vector representing our bond or our distance between our two objects, cross the vector for the linear momentum of the object rotating. Okay, so if I were to draw, let me just draw these vectors out a little bit for you. So let's imagine again that at the origin of our coordinate system, we have our proton, right? And we have this r vector, which is pointing in some direction towards our electron, which is this little red dot here. Okay, so there's r, and this electron is moving in some direction. Okay, I don't know which direction it is, but it's got some velocity vector. All right, or we could write me times the velocity vector of this atom, which is the momentum. Okay, and what we're going to do is we're going to take the cross product of these two. Okay, so let's say, and I know you guys are going to hate me for this. Everyone always groans when I do this. Right, so when we have velocity in this direction, so if radius is, let's say this is my radial vector. So here's my electron right here at the center of my, maybe I'll do it like this. Here's my electron right here at my knuckle. Here's the radius that's pointing to it. Let's say my electron is like right here. All right, so my electron, all right, let's do it a different way. I got to get it right. All right, so, geez, I always hate doing this. I'm trying to do the right hand rule, and I'm failing miserably at it. So the idea is that you have your radial vector. Okay, so we'll do it this way. And let's say, for instance, that here's your momentum vector in this direction. Right. So the electron is here, proton's right here, and the electron wants to move in this direction around the proton. All right. So the angular momentum is the cross product of this vector, the distance vector, with the momentum vector. All right. When you take a cross product, you get something perpendicular to it in the opposite plane. So these two vectors, v and r, they make a plane. I can try to draw it like this, right? They make this plane here. Right? And the angular momentum vector is going to be perpendicular to it, right? So if you have your velocity, if your velocity and your momentum and your position vectors are in the plane of my index finger here, your angular momentum vector is going to be out of the plane this way, right? The right hand rule. Right? So I cross them like this, and it's always going to be in the opposite direction. So the angular momentum vector is pointing out of the plane. It's kind of hard to draw. Something like this. Like that. All right, and L is the direction. The right-hand rule tells you which way it's going to rotate. So if L is out of the plane like this, then the system's going to rotate clockwise like this in the direction of your fingers. Right, so the net rotation along this axis of this system of the electron, due to this angular momentum, is an end-plane rotation clockwise around the proton. Right, so this is going to lead to, right-hand rule leads to clockwise rotation. And of course, the magnitude of the angular momentum vector is the mass of the system, right? The effective mass times the rate at which you spin it, right? So the harder we, right, and the momentum, that means that the angular velocity, of course, is proportional to the magnitude or the speed of the system, right? So the faster it's moving, right, the faster the electron wants to move in some direction, but of course it's attached to the proton by this chain, the R chain, or the R leash, if you will. It's going to want to convert that momentum into angular motion, so the faster it's moving, the more momentum it has, the faster it's going to rotate, which means frequency increases, angular frequency increases, and L gets bigger. All right, so L tells you something at fixed mass and fixed distance, how fast the system's rotating, how fast it's oscillating. So bigger the P, bigger the V, bigger the L, which means the bigger the omega. Again, it's not terribly informative, but it's good to keep these things consistent, right? So the idea is that if I like this picture a lot, actually. So the idea is that in 3 dimensions, we can draw our angular momentum vector if we draw it in a certain direction along the board. Pretty. I'm going to draw it like this to make it go into the distance. Right? The motion of the object lies in the perpendicular plane to it, right? So the proton, for instance, would be right here. And the electron is right here. Right? And the electron is rotating around this axis in the angular momentum at some velocity, at some omega. Right? And the net angular momentum is sticking out of this kind of donut. Okay, so of course, there's also implicitly inside of here a fixed coordinate system, a z and an x and a y, right? So L might not be lying across, L might not be pointing along one of the axes. It might be pointing in some random axis direction, right? So I can just kind of randomly draw my coordinate system here. And it doesn't really matter how I draw it, but the idea is if I draw it like this, right, maybe the coordinate system for the proton, or what we call the laboratory axis system, right? We put our hydrogen atom here in front of us in our lab, and we have an up, we have a down, left, right, and forward and back. Right, so these axes are laboratory axis. Right, but the angular momentum might be pointing in any direction. Okay? So I'm not really sure exactly which way it's pointing. Right, but we can measure how big L is, right, by measuring the energy. Right, remember the total angular momentum, L squared, right, the magnitude of the L vector, the energy of that is proportional, right, the value of that, or the energy of that angular momentum, is proportional to jj plus 1. The idea here is that the energy of J, which is proportional to L squared, the magnitude of L squared, or the magnitude of L squared, rather, is proportional to h bar squared j plus 1. Okay, so we can, our total angular momentum has some relationship to energy, right? We saw that. Remember that the kinetic energy is proportional to L squared minus over 2I. Right? So the energy is proportional to how long the angular momentum is. Right? So we can measure that. Right? We just spin it up. And what it says is that the angular momentum, the total angular momentum of our object, is quantized, right? It can only take values where J is 0, 1, 2, 3, 4, 5, 6, 7. Right? So that means that the allowed values of this allowed angular momenta, total angular momenta, are, where J is 0, that's 0. If J is 1, that's 1 times 1, h bar squared. J is 2, that's 2 times 3, that's 6 h bar squared. J is 3, 0, 1, 2, 3. 3 times 4 is 12, 12 h bar squared. And so on and so forth, right? These are the only allowed values of the angular momentum of this observation. All right, that tells you the length of this. Right, so the length of this vector is the square root is h bar times the square root of j plus 1. We just take the L squared and divide it by, take the square root of L squared. That's the length of L. All right, so the length of it is set by how much angular momentum you have or how much energy you put into it. The length of the angular momentum vector is roughly the square root of the energy. The more energy you put into it, the bigger the angular momentum is, as we expected. Okay, so J, the total angular momentum quantum number, measures either how much energy is in the rotation or how fast it's rotating, however you want to think about it. Okay? But what it doesn't tell us is about which way it's pointing. Right? As I said, the laboratory axis is completely arbitrary. The system could be processing any direction it wants. So we might want to measure that. We might want to measure which way the angular momentum is pointing. Is it rotating like this? Is it rotating like this? Is it rotating like this? And there's lots of different ways an electron can orbit a proton with respect to our laboratory frame. And we should, maybe we can figure out and specify that. And this is exactly where this other quantum number comes in. So if I were to redraw my coordinate system again, I'm just going to recenter it. I'm just going to shift all of my angular momentum vectors so they start at the origin, which is a free translation. So imagine we have this L vector here. This is our angular momentum vector of our electron. It's pointing in some direction. Right? We know that the length of L, the magnitude of this vector, is h bar squared, h bar square root j plus 1. Okay? So how do we measure which direction it's pointing? Well, we have to measure the components of the vector. Right? Because there's going to be, right? L is also written, can be written as a vector. Lx times x hat plus Ly times y hat plus Lz times z hat. Right? So there's going to be a component of the vector that we maybe can measure along each of the axes. So this is Lz. This is Ly, or Lx. And if we want to measure the y value, it's a little tricky to draw. I'm just going to project it along this axis and erase this. Sorry, my pen is freaking out. And this is, oh, that's too slow, sorry. And this vector along the y-axis is Ly, right? Oops, sorry. This projection along Ly is the y component of the angular momentum. Okay, so why don't we just go make a measurement of these components? We fix our axis system, and we ask the hydrogen, which way are you pointing, as you spin? Seems like a reasonable question, right? So we need to write down an operator. Right? We have an operator for L, the total magnitude, but we need to write an operator down for the direction, if you will, right? The components. But I don't have quite time to answer this question, but there's a big issue that we're going to hit. And this will be the kind of get us into ready for Monday. So here's a big problem. We can only measure one component at a time. All right, next class we'll talk about this more mathematically. All right, it's a really, really super critical point. And in fact, it's the exact reason we'll see when we get to spin in a little bit. We'll apply this to spin. Why color and flavor in our old electron box of problem set 1 are not compatible measurements. So the source of that is the source of this, because of this. That we can, it turns out that we can't measure all 3 directions. We can't know the direction of the axis of the angular momentum vector. We can't tell you which way it's pointing. We can only determine one of the 3 components. So we can either measure, and I can't prove this yet, we'll prove it next class. We can either measure L squared and LZ together, or L squared and LX together, or L squared and LY together, but not LX and LY, or any combination of the directions. Right? You can't measure 2 directions at once. You can only measure 1, or any other combination. All right, so we have to make a choice. I haven't proven this yet, again, so just bear with me. But the fact of the matter is I can only pick one of those 3 pairs. If I know L squared, if I wanted to find L squared, which was my energy, I better know that, I can only know LZ, LX, or LY. Can't know all 3. I have multiple ways to prove this to you online. Show you it classically, because there's a classical analog to this. And I'll also show it to you quantum mechanics. So the typical choice, so the convention is that we choose L squared and LZ. Okay? And they each have operators. So the L squared operator, we already know what it does. If you apply it to psi, you get h bar squared j plus 1 psi. And when you measure LZ, right, the z component of psi, you get h bar m psi. This is where the m comes from. The other quantum number. So you have this one, the total, this is the total angular momentum quantum number. And this is the projection quantum number. Okay. So these are where the 2 numbers come in. The only things that we have to have 2 numbers. This is why we have 2 numbers, because there's only 2 things we can measure about angular momentum. We can measure the length of the momentum vector, the magnitude or the energy, which is j, and we can measure one of the directions, which is m. All right? We'll look at the rules of this a little more, and then we'll draw the vectors and stuff on Monday, and I'll show you quantitatively and qualitatively why we can't measure all 3 simultaneously and the consequences of it. Okay, so we'll come back to that on Monday. All right, have a good one, everybody. Exam will be posted in 15 minutes. So good luck, and feel free to send me questions if you have any questions.
I was going to type in chat, but I meant to talk to you right here. So I was thinking on Monday, I could give out like more cards that we would obviously talk about for each player on the team, just saying like